Welcome back, folks. I want to welcome you to another video. This time in this video, we're going to be discussing hypothesis tests for a population mean of one sample. So I had an earlier video where I went over kind of the overview of a hypothesis test. Remember, it's just a way of testing if there's a significant difference in a population parameter. In an earlier video, we went over the population proportion. In this video, we're going to talk about how do we test if the population mean is significantly different than a value. Okay? So let's kick things off by talking about what are the conditions necessary for a hypothesis test for the population mean. Well, in order to do that, we need to satisfy, the central limit theorem for means. And so that boils down to an independence assumption. And I know you guys are so sick of this, but what are the things we check for independence? We always look for to see if the samples were collected randomly. And we also see to check if we have sampled less than 10% of the population. If both of those are satisfied or can be reasonably or plausibly assumed, then we say the independence assumption is met. And then for means, if you recall, we also needed, instead of a success and failure condition that you needed for proportions, we needed a nearly normal condition for means. And the way that that works out is that for sample sizes that are small, typically less than 30, we consider that to be small, what we need is the data to be unimodal and symmetric. Okay, because if you recall, the mean, we're going to be using the t-distribution. And so the t-distribution works best whenever our data is unimodal and symmetric. However, due to the nature of sampling, for larger sample sizes, let's say we're bigger than 30 or 40, let's say, we can relax those unimodal and symmetric requirements. Unless the data is like really skewed or there's a bunch of outliers. But generally what happens is, guys, we have what's called sampling variability every time we take a sample. So basically we're saying if we take a large enough sample size, we're going to mitigate or remove some of that sampling variability. Okay? All right, so once we have checked the conditions, how do we actually perform the hypothesis test for, not for proportions, but for means? Okay, right off the bat, we are going to notice, let's make this a little bigger. Right off the bat, we notice that our hypothesis no longer includes the parameter p, because we're talking about the population mean. We use that Greek letter mu. Okay, so that stands for population mean. And so our null hypothesis, as we know, will always be equals to, so the mean will be equal to some specified value, okay, some number. We call that mu naught, and that number is the hypothesized mean. So that's your null hypothesis, always an equals to. The mean will equal to some number. On the other hand, your alternative hypothesis has three different possibilities. Either you can have what we call a right tail test, that's where the mean is greater than that value. We could have a left tail test where the mean is less than some value, or we could have a two tail test where the mean is not equal to some value. So all of those kind of depend on the scenario that you're in. And once again, we've talked about this in previous videos. Hopefully you're comfortable knowing which alternative hypothesis to select for your scenario. So after we write the hypotheses, we could check the conditions. As we mentioned earlier, there's an independence condition that must be met via randomness and sampling less than 10%. And then we have to check the nearly normal condition. If we're smaller than 30, let's look for a unimodal symmetric distribution of the data. If we are greater than 30, we can kind of proceed because we can relax those assumptions. Once we have the conditions checked, we can now calculate the test statistic. Okay, so the test statistic for a hypothesis test for the means is going to be a t-test because we are using the t-distribution, much like what we did when we did confidence intervals for the mean. The test statistic will be x bar, where x bar is your sample mean, minus the hypothesized mean. So mu naught is the mean that's in your hypothesis, the value that's in your hypothesis. And then we divide it by the standard error. So in case you guys forgot, the standard error from the central limit theorem says it's the sample standard deviation divided by the square root of n. Okay? Sometimes you'll see the notation SE instead of standard error, but just know it's S divided by the square root of n. So basically what we're doing is we're taking this X bar, this mean, and we're converting it over to a t-score. Okay? And also keep in mind, guys, when you are dealing with the t-distribution, don't forget it's based off of degrees of freedom, which will be one less than your sample size. So your degrees of freedom is n minus 1. Okay, once we have our test statistic, we're then able to calculate the p-value. And so just a little reminder here, the p-value is the probability that you get your sample value, in this case the sample mean, or something more extreme, given that the null hypothesis is true. So we're saying, what's the probability that we observe or we get this sample mean, assuming that the null hypothesis is true? Okay? Remember, a large p-value corresponds to, it is very likely that we get that sample data. Okay? Small p-value indicates that it is very unusual or very unlikely. Very unlikely that we observe this data. Okay? And remember, your p-value, it's a value, so this just means n. Don't worry about the notation. It has to go between 0 and 1. Okay, remember your p-value has to be between 0 and 1. The closer it is to 1, the more likely it is for us to observe that data, assuming that the null hypothesis is true. The smaller the p-value, the less likely it is for us to observe our data, given that the null hypothesis is true. Once we have a p-value that is calculated, we compare it to our level of significance. Okay, I'm in step 5 here. Remember, alpha is the level of significance. Basically, it's the probability of an error. We want to make sure that for us to say that the null hypothesis isn't true, we have to make sure that we're below that error. We want to be really, really sure. So if our p-value is less than alpha, we reject the null hypothesis. Okay, so what's the connection there? Remember, small p-value means it's very unlikely for us to observe the data given that the null hypothesis is true. So therefore, if it's very unlikely, that means that, oh, well, the distribution of the null hypothesis, or whatever the null hypothesis is saying, is not true, because it's very unlikely based off of what we've seen in our data. So if the p-value is less than alpha, you reject the null hypothesis. On the other hand, if the p-value is greater than alpha, we do not reject the null hypothesis, okay, or fail to reject the null hypothesis. And then once you've made that decision, you can make your conclusion. So if we reject the null hypothesis, that means that there is significant evidence that H null is wrong and HA, the alternative hypothesis, is correct. So when you reject the null hypothesis, there is significant evidence. However, if you fail to reject the null hypothesis, there is not significant evidence. And we've talked about this in previous videos. The easy way to remember this is anytime you fail, that means there's not enough. Okay? All right, so that's a quick little run through on the steps necessary to perform what's known as a t-test. This is called a one-sample t-test if you go on to other classes. But here, let's actually get into an example, and let's see if we can figure out how to do this by hand. And then I'll show you how to do it using a bit of technology. All right. For example, housing prices in the U.S. in 2021 had the largest jump in 30 years. Recently, in one large community, realtors randomly sampled 36 bids from potential buyers to estimate the average gain in home value. The sample showed an average gain of $9,560 with a standard deviation of $3,200. Determined using a level of significance of alpha 0.05 if the population mean gain in home value is more than $10,000. Okay? So what we need to write here, first step, is just write our hypotheses. They want us to test if the mean gain in home value is more than $10,000. So that means our null hypothesis will include the population mean parameter, the Greek letter mu, mu, and the null hypothesis will always be an equals to. So the null hypothesis saying nothing has changed. So the null hypothesis will be that the mean equals $10,000. On the other hand, the alternative hypothesis will be that the mean is greater than $10,000. Why is that? Because that's what we're testing. We're seeing if the home value, the mean gain in home value, is more than $10,000. Okay? All right, next, let's check some conditions. All right, let's start off with independence. All right, there's two components we can use to check for independence. We could check the randomization condition. Let's see, did we perform a random sample? Yeah, they tell us we randomly sampled 36 bids. So we have randomness. And do we have less than 10% of the population sampled? Absolutely. We've only looked at 36 houses out of all the houses in the US. That is way less than 10% of all possible houses. So independence is satisfied. Okay. Next, let's check the nearly normal condition. Nearly normal condition. Well, this one, it's a little tougher to check, right? So we don't actually have all 36 of the data. It will be nice if we have the data and we could look at a histogram and then be pretty sure here. But what we're going to have to go off of is the fact that we have a sample size of 36. We're going to typically say that that's large enough for us to say that we're going to be nearly normal. So remember, the condition is if you're big enough, you don't have to worry about unimodal and symmetric. So we're going to say it's plausible. And what I mean by that is that it's possible for this to be nearly normal because our sample size is greater than 30. Okay, so we can say, yeah, we're nearly normal. We're not 100% definitely sure it's normal, but it's plausible, right? It's reasonable to assume. That's a better way of saying it. It's reasonable to assume that it's normal because the sample size is big enough. All right, conditions are met. Let's keep it moving. Next, we need to calculate the test statistic. Calculate the test statistic. Okay, well, I'm going to rewrite the formula for your convenience here. So our test statistic is X bar minus the hypothesized mean over the standard error. Where the standard error, remember the standard error was equal to the sample standard deviation divided by the square root of n. I'm just going to plug that into this formula. All right. So let's go ahead and get some values here. So our test statistic for this t-distribution will be X bar. What was the sample mean from those 36 bids? It was 9560. So we take 9560 minus our mean from the hypothesis, which is $10,000. So 9560 minus 10,000 over the sample standard deviation, which is 3,200, divided by the square root of the sample size, which is 36. So I'm hoping you guys are able to understand where we're pulling those values from. Let's go ahead and get us a test statistic to, let's say, let's do 3 decimal places since we're going to use a bit of technology. So we're going to go to a calculator. Okay. I'm going to do open parentheses, 9560 minus 10,000. Divide that by the sample standard deviation. Oh, just do open parentheses. Sample standard deviation, which was 3,200, divided by the square root of 36. All right. Let's get out of that. Close that one up. And there we go. To 3 decimal places, we get a t-score of a negative 0.825. Okay. What does this mean? This means that the data that we got, the tested, the sample mean that we got, 9560, is 0.825 standard errors to the left of the hypothesized mean of 10,000. That's what that means. Okay. So the question becomes: is that enough of a difference to reject our null hypothesis? Well, in order to figure that out, we're going to calculate the p-value. All right. So the p-value will be, we have a normal looking distribution, but this time these aren't z-scores, these are t-scores. All right, but we're still centered at t equals 0. And then we're going to apply our t-score of a negative 0.825, which would be over here. So this is t-test, negative 0.825. And we are going to shade in which direction do we shade? Do we shade to the left or to the right? In order to figure that out, we go back up to our hypotheses, and remember it's the HA, it's the alternative that tells you which way to shade. So we need a shade to the right because this is what we call a right-tailed test. We're going to the right. Okay, so that means our area, aka our p-value, will be all of this shaded area to the right. So all of that shaded area to the right is the p-value. Okay, how do we figure that out? Either you can use your t-tables, or we could use a little bit of technology, and that's what we're going to do here. So let's go over to StatCrunch. Okay. We are going to go to Stat. Hoping you guys can see this. And then we're going to go to Calculators. And then we're going to go to the T calculator. Remember, this is the T distribution. Okay. So let's come here. Let's zoom in a little bit. All right. So in order to calculate the probability here, we need to know the degrees of freedom. Well, remember how our n was 36? Well, that means our degrees of freedom is 36 minus 1, or 35. Very important that you get the correct degrees of freedom. So we're going to put in 35. To our degrees of freedom. We're calculating the probability that our t-score is greater than, so switch this over to a greater than, and our t-test, remember our t-score was a negative 0.825. Let me get rid of my 0 there. All right, there we go. That looks good. Let's go ahead and compute this. And there we go, folks, to 3 decimal places. Let's call it a 0.793. Approximately 0.793. All right, so that is our p-value, 0.793. Remember, p-values go between 0 and 1. Okay. Lastly, let's make a decision and write the conclusion in the context of the problem. Let's talk about the decision. To make the decision, you take your p-value and you compare it to your alpha, your level of significance. Well, our p-value was what? 0.793. And they told us earlier in the problem to use an alpha of 0.05. Right, which is the most common alpha to use. And then I'm just going to add a 0 at the end here just to make it easy for comparison's sake, which is perfectly legal. You can add as many zeros as you want to the end of a decimal, and it doesn't change the decimal. So yeah, it turns out 793 is certainly greater than 0.050 or 50, right? So that means our p-value is greater than alpha. And what does that mean once again in the context of this problem? It means that assuming that the null hypothesis is true, assuming that the mean home gain is $10,000, right? The probability that we get our data that we got is very likely, okay? So that means we should not, do not reject the null hypothesis. Okay? Once again, that's because this p-value is sufficiently large, is big, right? So that means it's likely for the null hypothesis to have the right distribution there. So we do not reject the null hypothesis. So what does that mean in the context of this problem? This means that anytime we do not reject the null hypothesis, that means that there's not enough evidence, or there's not sufficient evidence. So there is not sufficient evidence to state that the population mean gain in house values is, and then let's go and check. What were we trying to test? That comes from your alternative hypothesis. We were trying to test if the mean was greater than $10,000. And so by us not rejecting the null hypothesis, we're saying there's not enough evidence to say that that's true, that the mean is greater than 10,000. So there is not sufficient evidence to state that the population mean gain in the house values is more than $10,000. Okay. So that's like the full hypothesis test for means procedure by hand. Okay. So, guys, what we could do though is we can use technology to kind of speed this up a little bit. And specifically what the technology is going to help us do is going to help us calculate this test statistic very quickly and get us the p-value very quickly. So however, my disclaimer is the technology will not help us write hypotheses. It will not help us with the interpretation and the decisions. That is still up to us. All right. So please make sure you go through previous videos and understand when do I reject a null hypothesis, when do I do not reject a null hypothesis, and then understand the corresponding interpretations of those decisions. But let me show you quickly how to do a t-test in the calculator using the information that we have. So what we do is, all right, let's get out of this. Kind of ignore my data here, but what you do is when you want to perform a t-test or a test for the mean, you go to t-stats, we go to one sample, and when they give you the mean and the standard deviation already, that is with summary. So we're going to go with summary. And this should look very familiar. We did the same steps whenever we did a confidence interval for the mean of one sample. So what was our sample mean? I believe that was 9560. Okay. Our sample standard deviation was 3200. And our sample size was 36. Okay. Now we're going to perform a hypothesis test this time for the mean. And our null hypothesis was that the mean equals $10,000. So we're going to type in 10,000. And our alternative hypothesis was that it was more than 10,000. So make sure you select the correct one. That's all you got to do, folks. We go to compute. Drag this over for you guys. And boom. Hopefully you can see this here. We get a t-stat of a negative 0.825, exactly what we calculated by hand. And we get that p-value of 0.793. Okay. That standard error of 533.33. Remember, the standard error for means is the sample standard deviation divided by the square root of n. And then they're reminding us that since this is a t-distribution, our degrees of freedom is one less than our sample size of 36. So that's a quick way, guys, of getting your test statistic and getting the corresponding p-value. Okay. All right, let me give you one more question here and we'll wrap this one up. So, for example, does the expectation of good weather lead to more generous behavior? Psychologists study the size of the tip in a restaurant when a message indicating that the next day weather would be nice was written on the bill. Okay, so the server handed the bill and she wrote, it's going to be, hope you enjoy tomorrow's sunny weather. The tips from 20 customers measured as a percent of the total bill has been loaded into StatCrunch. So we have the data, and the data is going to be percents of the total bill, right? So if you tip 20%, you're going to see 20 in the data table. If you tip 15.9%, you're going to see 15.9. Test using alpha 0.05 if the population mean tip percentage is more than 21 when the server writes a message about good weather on the bill. All right, so we are going to go through all the steps necessary to perform this test. First step, let's write our hypotheses. The null versus the alternative. Since we're talking about population means, mu is the parameter of choice. And the null hypothesis will be the mean equals that 21%. So since our data, folks, is going to be, let me show you the data really quick. You've already kind of seen it. You see our tip percent data here? You see how even though this percent is written as 20.8%, so that indicates that our percents aren't written as decimals. What I mean by decimals is like 20% is 0.20. So just go off of the scale of your data, right? So since my data are written in this scale, that means that my hypothesis will be 21 instead of a 0.21. I hope that makes sense. All right, so then that's our null hypothesis. Our alternative hypothesis is whether it is more than 21. Okay. All right, so now we have our null hypothesis. Let's quickly check our conditions. Okay, so checking conditions, I'm gonna do that over here. Independence. Okay. Let's see here. We need a random condition, and we need a less than 10% condition. Okay, random condition. Now, excuse me, they don't explicitly say that this was a random sample, so we cannot assume that it's randomness, but it's reasonable to assume, right, that at this restaurant we're going to get a good mixture of tips, right? So reasonable to assume, even though it's not explicitly stated. So we're not definitely sure that it's random, but we can be reasonable and assume that it is. And then less than 10% certainly is less than 10%, because we've only looked at 20 customers, and hopefully 20 customers is a lot less than the number of people that come to this restaurant. So the independence, I think we can say it's good to go. Okay, now the nearly normal condition, what we'll have to do is we'll have to look at the histogram of these, because our sample size is 21, which is on the small-ish side. So what we'll do is let's look at the histogram really quickly. So if you guys remember to get the histogram, in StatCrunch we go to Graph, Histogram. All my items are in column called Variable 1. All right. Let me see here. Let me make this smaller. Okay. Let's see here. Click on compute, and there is our histogram. And yeah, our histogram looks to be certainly unimodal, and it looks to be pretty symmetric. Okay. So the histogram is unimodal and symmetric, so we are good to go. So we are nearly normal. So the conditions are met. Okay, now the next thing we're going to do is we're going to do this in StatCrunch, guys. So let's just grab the information that we need to know, right? So we know we need a sample mean, right? And so actually, no, we don't need a sample mean. Excuse me. That's going to come from our data. So what we need to know here is that our hypothesized mean is that 21. So just keep that in mind, okay? All right, but as far as doing this in the StatCrunch, very, very, very straightforward. Here we go. We're going to go to Stat, go to T-Stats, one sample, this time with data. Okay, we got variable under items. I don't know if you guys can see this. Let me shrink him a little bit. Under columns, we're going to select variable 1. And then we're going to do a hypothesis test. And our mean is going to equal 21 for the, what is that? 21. Okay. And then our mean is going to equal 21 for the null hypothesis. And our mean is going to be greater than 21 for the alternative hypothesis. That's it. That's all we have to feed the calculator. It's going to go through. It's going to calculate the mean of that data set. It's going to calculate the sample standard deviation of that data set. It's going to do all the work for us behind the scenes. And here we go, folks. We have a test statistic of 2.76, let's say, and a p-value of 0.0063. So our p-value is 0.0063. So what we're going to do is next compare that p-value. Going to compare it to alpha, which is 0.05. Just going to add a couple of zeros here. So the question becomes, how does the p-value compared to alpha? Well, it is less than. 63 is less than 500. So when the p-value is less than alpha, that means we should reject the null hypothesis. In fact, you see how small the smaller your p-value is, the tinier it gets, the stronger your evidence is. Like, we have really strong evidence to say, yeah, the tip percentage is more than 21%. All right, and so that leads us to our interpretation. So there is, if I could spell, there is enough evidence or sufficient evidence to state that the population mean percentage of tip is more than 21%, because remember that was our alternative hypothesis, when the server writes good weather on the bill. Okay? So basically, if you're in the restaurant industry, write good weather on the bill. That's what this is telling us. You're going to get more than 21% of this. All right, guys. I know that's a bit on the longer side, but hopefully I went through and you're able to see how to do these both by hand and via using technology. I very much look forward to seeing you guys in the next video.